right, welcome everybody to today's webinar. Today's topic is going to be machine learning for accelerated aerothermal design in the age of electromobility. Now, today's a little bit different. I'm not going to be giving the webinar. Instead, we'll have my colleague Eugene de Villiers give the talk today. Before he begins, let me kind of kick off with a little bit of information. So some of the webinar goals today, we want to introduce ENGYS and artificial intelligence for engineering applications, and outline the UPSCALE project and how we plan to incorporate AI into the vehicle aerothermal design process, and provide a little bit of, some preliminary design or preliminary results in the aerothermal machine learning efforts. Now, in terms of questions, we'll answer all the questions at the end and continue via email post-webinar. What you can do, if you do have a question, you can reply to the webinar invite, and that will go directly to me, and I can organize an answer and reply to you. Just a little bit of information about ENGYS. We are global providers of CFD products and services. We were founded in the UK in 2009, so we're celebrating 10 years of being in business. We've always had a focus on enabling open source software in industry, and we've had extensive experience with foam and open foam. If you're familiar with open foam, you know that it came out around 2005, 2006. But before that, there was another code called foam. So we've had experience with development in that code base since 1999. We have 7 offices worldwide in the UK, Germany, Italy, here in the US, Australia, South Africa, and Brazil. And we have an established network of distributors around the world in Japan, South Korea, here in the US, France, and also in Spain. Just a little bit of information about our products. We have Helix, which is a general purpose open source CFD software suite. Then we also have Elements, which is a superset of Helix, and it's more focused on advanced open source CFD for the automotive community. So automotive design, external aero analysis, things like that. Adjoint related features inside of Elements adjoint add-on. Then we also have Helix add-ons, which include adjoint optimization, so a continuous adjoint optimization. We have block coupled solvers. We also have an add-on for marine hydrodynamics modeling and also advanced multi-phase flow modeling. And then last, we have Helix OS, which is an open source GUI for standard open foam. You can download that last one for free by going to our website, ENGYS.com, and look at our products, and you can find the download link for Helix OS. In terms of upcoming conferences, you can find out lots of information at ENGYS.com/events. And if you're looking for a conference to attend this summer, you can look at the 15th Open Foam Workshop being held here in the US. It's in late June, and ENGYS is currently the official sponsor of Open Foam Workshop 15. If you're in Brazil, you can attend the Brazilian Congress on Computational Fluid Dynamics, which is also sponsored by ENGYS. And then finally, if you're not going to attend an event, but you would like to attend something virtually, you can also look at these events on ENGYS.com/events and find an upcoming webinar on cloud computing with Helix and Penguin Computing on Demand, which is on March 26th. And then also we're kicking off our adjoint April with enhanced topology optimization with multi-objective continuous adjoint. That is on April 7th at 10 a.m. Central Standard Time. You can find out more information on our blog. You can subscribe for updates. You can see R&D notes, past webinars, continuous adjoint information, related content. All right, let me kick this over to my colleague. So Eugene is one of the founders of ENGYS and also managing director of ENGYS. And so he'll be giving today's talk.
Thank you, Dan. Can you see everything clearly? Okay, I'll just assume everything's working and go ahead. Thank you very much for coming today. I'll be talking about our efforts at ENGYS, working on machine learning for aerodynamic design. Now, before we jump into the bulk of the talk, I just like to give you a quick summary here. We're not talking today about new methods in AI. We're talking about using existing methods that have been published in AI or neural network modeling of flows for vehicles and vehicle design. So it's a novel application, let's say, rather than novel use of neural network systems themselves. So I'm going to skip through the abstracts, through the contents. I start this presentation with just a few bytes or information bytes surrounding this field. It's been increasingly visible and increasingly busy field. There's an enormous amount of research, and I just want to share some thoughts with you about neural networks and artificial intelligence. And first of the question when I started preparing this presentation is why do these things actually work as well as they do? Where does this all of a sudden appear from? And of course, there's the history in the 80s. Started off with the basic modeling, but when you dig down into it, what is the underlying reasons why these artificial intelligence systems, these neural networks, really work? If you pick apart the name ANN, artificial neural network, you can start to find some of the clues. So first you have artificial, so that's something made by humans as a copy. So it's not something made from scratch. It's something that mimics something in the natural world. Secondly, the neural, it's obviously to do with the nervous system, with brains. And then network being a group of systems that interconnect things. So the name of the system clearly defines a lot of what it's about. Now, if we look at the source of this inspiration, it comes from the human brain, and that obviously has evolved over a very, very long time to predict and conversely understand, to some extent, the universe we live in, so we can interact with it and move around and affect things. And so, because of this, we're basing our artificial neural networks on real ones. We expect them to have some similar characteristics. And so the fact that actual neural networks in our brains work means that artificial neural networks work for a similar reason, and that's because they were evolved. They were evolved to work within this universe that we inhabit. Now, there are some interesting things about physics and the universe that make neural networks particularly effective. I've read a few books about this. Now, I'm by no means an expert, but when you look at a lot of the physical models, the things that tie our universe together, a lot of it can be described, at least at a human level, through relatively low order functions, polynomials of around order 2 to 4. So it's not, the functions that describe the universe are not incredibly complex. They tend to be more built up. The complexity tends to be a build-up of simpler functions that are combined in a hierarchy, and that's mirrored really in the context of neural networks. Neural networks, there's a universality or universal approximation theorem that is related to neural networks that say that neural networks can approximate any continuous function in a predefined range. And since the universe is described by these, or predominantly described by these polynomials, that means that neural networks are very well suited to model the universe as we see it. And neural networks also is a combination of layers. Just like the universe generates complexity from hierarchy, neural networks have similar characteristics to produce complexity. So the second reason neural networks seem to work is because neural networks work in a similar way to which our universe actually is put together. So that's quite interesting. As I mentioned before, the neural networks, artificial intelligence, deep learning, these things have actually blossomed in the last few years. Probably many of you here are actually working in the field and are well aware of this. I did a little search on arXiv, just looking for the keywords machine learning and or deep learning in the title or abstract. So this is not a total list of all publications in this field. It's just let's say a sample, a proportional sample of how things have changed. And if you look at the graph on the right, you can see the rate of change of publications. 2009, there was a couple of dozen. And last year, actually 2019, it was more than 14,000 publications. So year on year, we're looking at about an 80%, almost doubling in the number of publications per year. So there's clearly an enormous amount of interest. And you can see from the applications starting to emerge that there's a real potential here. So I think the investment is warranted. There's some interesting things that will emerge over time from this research. And there's already a lot of applications that we're using now. I mean, the examples such as Alexa and self-driving, they're at the top of the list, but there's an enormous number of additional functions that are being driven by this technology. So one thing that's in our field in engineering that is that's become very clear, and there's a lot of publications in this context, is that you can use these artificial neural networks or machine learning to reduce the requirement for domain expertise, where you would normally have to be, let's say, a specialist in turbulence to be able to make a better turbulence model. By leveraging something like machine learning, you can very quickly make small improvements or even quite considerable improvements without having an enormous amount of domain expertise. It doesn't mean with domain expertise you couldn't do better, but it just means that the barrier to entry to actually make something that has a real contribution is much lower. In addition to that, and it's another thing that I think drives this increase, is the availability of high quality tools. So things like TensorFlow, PyTorch, there's lots and lots of other examples. These environments have made it much easier for a layman, a new entrant, to become proficient and to start using this functionality. These models are also very performant. They can take a small fraction of the amount of time required for a full physical model. And they're also very automatic. So you don't have, there are some, of course, choices to make when you're creating machine learning models, but by and large, those choices are limited in scope. It's not similar to the way in which you would do curve fitting, where you have to choose the function. No, I mean, here you choose parameters, let's say number of layers, number of variables, and so on. So the choices are somewhat simplified, and the functions are more universal. So the entire system has just led to an explosion that you see on the right, and I think there's quite a lot more to come in this context. So one of the examples I mentioned is the turbulence modeling, and we've had some experience here at ENGYS developing a new turbulence model, or at least implementing a new turbulence model, working and talking to the original person who derived and implemented many of these functions. We're talking about the EB-lag turbulence model here, and the amount of time that you have to invest in learning about turbulence, in terms of implementing the different physics, in terms of the different discretization, so on, is enormous. It can take years and years just to make one new turbulence model that is X% better than the previous one. And the reality is that using machine learning methods, you can probably get a comparable gain, at least in a limited set of applications, much more quickly. So in terms of theory and practice, this technology, I think, is very powerful. I named this whole section the data physics continuum. It's a bit pretentious maybe, but the idea was that we came to realize very quickly is that machine learning isn't something that just sits at one end of opposite to a physical implementation. There's a whole spectrum really of integration between what we call physics-based modeling, or something similar to CFD, that is our main focus at ENGYS, and data-driven methods like neural networks. So you can have pure data-driven methods where you just say, here's a picture, and it looks at the picture and says, that's a cat. That's pure data. There's no integration between data and physics there. At the other side, you could have something like a CFD model where every pixel is defined, all the flow, all the physics is represented at some level, and then it produces something at the output. But in between those extremes, I don't know if they really are extremes, but we see them that way. There's this whole continuum, this range of integrations between physics and machine learning. And some of the work we're doing in the context of AI fits into different parts of it. We work at both extremes, but also we're starting to look at the bits in between. So with an example of turbulence fresh in my mind, this is something called data-driven turbulence modeling. This is a huge field huge. It's a very fast-growing field. A lot of people have an enormous amount of interest there, trying to extract correlations from turbulence results using machine learning. And I think there's quite a lot of success and quite a lot of interest in pushing it further. There's data-driven ODEs or methods to solve ODEs and PDEs using neural networks. There's also something called physics-guided neural networks, where you encode some of the physical underpinnings of the models into the neural network system as a constraint or as an additional objective. So these are just a few examples, but really there's almost a continuum, a smooth interaction between the physics-based modeling, or the pure physics-based modeling on the one end, and the data-driven models. So there's many opportunities for optimization, many opportunities for producing more efficient systems where you have some combination of physics-based, mathematics-based modeling and data-driven models. Generally speaking, we have this trade-off where the cost of physics-based modeling tends to be higher. The cost of data-driven methods tends to be lower. That's why we want to incorporate them, because we can get solutions much quicker. Accuracy tends to have the opposite trend, but it's not always the case. So there could be islands where data-driven methods can be particularly accurate, and it really just depends on how detailed your training is and what level of integration you have. So obviously we're trying to get the best accuracy for the lowest cost. That's the reason that we're looking into these methods. So a lot of our exposure to AI, to machine learning, has started with a project called UPSCALE. This is a European Union-funded project that's called UPSCALE because of the acronym relates to upscaling product development, simulation capabilities, exploiting artificial intelligence. It's a lot of artificially injected words to make up a word that comes easily off the tongue in the form of UPSCALE. So the organizers claim it's the first EU project that has the specific goal to integrate AI into traditional computational computer-aided engineering software. I don't know if that's true, but so far the research seems to prove that out. I think there's a lot of other projects picking up the same thread now, and of course there are many other research initiatives outside of the EU project context that have already done something similar. Our nominal objective here is to apply machine learning to reduce the development time. This is the pre-production, the vehicle design and production, or at least design component, by about 20%. So this is specifically in the context of EVs. We want to focus also in this context on thermal, Aero-Thermal, and crash, because those are the parts that take up the most cycles on HPC. So if we look at typical HPC utilization inside an automotive company, we see that Aero-Thermal and crash, they take up way more than 50% of the total HPC cost. So if we can substantially reduce the cost of that and substantially shorten the cycle, the design cycles between various engineering systems, then we can reduce the overall cost and time to market of these systems substantially. So at the same time, as we want to reduce the development time, we also want to reduce simulation times, improve accuracy, and so on. And we can do that simply by trying to learn, by accumulating more and more, in quotation marks, experience into our neural network systems, our artificial intelligence systems, and trying to reuse more of the components, more of the modeling that we have to calculate anyway. So we're trying to extract more value from the various physics-based modelings and augment them in ways to make them faster and more accurate. So here's a list of the participants. I'm not going to go through all of them, but you can see there's some major automotive OEMs involved, as well as very highly ascribed universities, VUB, ESI, Volkswagen, etc. So as I mentioned, there's two specific components that UPSCALE, the project, will focus on. There's the CFD aspect, where we are heavily involved, and there's the crash part, where we're not participating. So I will focus here exclusively on the CFD part. The crash is half the project, more or less, and it has similar goals to the CFD part. So in the context of electromobility, in the context of EVs, we have some new elements to the vehicle design that haven't been there in the past. So some of the experience, at least a portion of the experience that applied to designing cars, passenger cars specifically in the past, has somehow become less relevant. And we have new parameters, new components that have increased importance. And so there's less experience on how to integrate the systems, how to build aerodynamic shapes, how to integrate battery packs and cooling systems into the aerodynamic design. And in that context, it was felt that pushing AI and machine learning into the process early on could speed up the time to get to a more optimal solution in this context. So we'll use AI then in this context to, number one, to predict the flow fields and the aerodynamic forces by purely data-driven methods. So we wanted to train neural networks on different shapes, different vehicles, and allow them to provide us with very quick, low fidelity flow fields and force estimates on the vehicle, so we can have a quick iterative solution process. In addition, we want to do something called automated geometry parameterization. This is in order to help improve the accuracy of some of the AI methods, but also in order to generate more cases in a more automatic way to create training data for the AI systems. Further on, there are some components of the project that want to work on that spectrum I described earlier, that continuum, where we want to use AI methods to enhance the CFD solvers. This either to make them faster, to make turbulence models more accurate, or to make initialization, for example, more robust and closer to the eventual solution. We probably will not in the end use neural networks to augment the ODE solution. We're using coupled solvers instead, which is proving very efficient. But the data-driven turbulence modeling is certainly high on our priority list. Then, of course, there's some battery components. The battery pack and battery cooling in the context of the Aero-Thermal is more of a constraint, i.e. we have to have enough cooling flow through the radiator in order to cool the battery pack. So there are some reduced order models attached to that to make that feedback loop, or to close that feedback loop. Okay, so the component I will focus on today, I mean, there's a lot of different CFD parts to the project, but the one that is the focus of this presentation is the concept of real-time CFD, or functionally to allow designers who are not engineers specifically involved in aerodynamics to get a real-time feedback on what their design choices mean for vehicle efficiency in the form of CO2 and range and so on. So that's what this slide is about, is the idea that in vehicle design, the shape and the process and what it looks like is still very strongly influenced by aesthetics. So it's not pure optimization in terms of performance. There needs to be a human there, and they need to have a subjective opinion of whether a particular shape is going to sell or going to look nice. And so because there's a human in the loop, we can't run a pure optimization strategy based on some physical characteristic. We need to filter the data through a designer's mind, and because of that, there's some fundamental restriction on how parallel you can make the process, on how quickly you can feedback the loop. So the idea is that we have this real-time capability that we train beforehand. We take hundreds of sample geometries, so mostly similar to what we expect to come out the other end. We run a DOE on those different samples, and then we train either a neural network or a reduced order model, or both. We're doing both at the moment to try and make a response surface of the design space, and then that model will act as a real-time feedback to the designer in order to get some estimation of how the vehicle performance and different flow field characteristics will change as he changes the design and the aesthetics of the vehicle. And hopefully through that, we can of course speed up the feedback loop. The engineering happens upfront rather than in a human interrupted loop, and then the whole process should be considerably faster than it is currently. So this is the offline training component. This diagram, I don't have to look at all the little plots and parts. It's just really a diagram of how the data will move and what components will be where and how they fit together. So basically we have an aim of building neural networks to predict the flow field, the pressure, and the drag on the vehicle. And then we can do that based on low fidelity data, that would be RANS, steady state, or high fidelity data, that would be LES or DES. We have other components such as geometry, parameterization, and so on that feed into it, but essentially we have different strategies for generating data of different fidelities that have to go into the training system, then be trained to create a neural network model. In the same time, as a separate system, we also train a battery reduced order model that will allow us to judge whether there's sufficient cooling flow for a particular battery pack, a particular driving cycle. So once we've got these neural networks, these models, then we can go to the online workflow, and that's what this diagram depicts. So functionally, you have the designer in the loop here. It's the red hexagon. He generates a modified geometry. The geometry goes through a filter that will turn it into something recognizable to the neural network, in this case, a level set. That field is sampled, goes into the neural network, it produces flow fields, it produces a parameterization. These in turn produce drag coefficients, and that then gets fed back via a real-time error interface to the designer. So you can see his changes reflected in the performance metrics of the vehicle. In between, there's the battery reduced order model to tell you red, green, your performance of the battery cooling system is working out or not. So I mentioned that there are other components of the upscale. There is several tasks, several work packages inside the context of the project. I'm just going to quickly introduce a few of them. There are specifically here that I'm going to talk about are the different augmentations to the solver. So the first one is the accelerated flow solver, where we're a lead on. And we initially started working on accelerating the fluid flow solver through convolutional networks directly inside the pressure solver. So the idea was that you create your normal algorithms for solving the flow, and then instead of solving a very expensive Poisson equation for the pressure, you use a neural network to predict, at least for some iterations in the cycle, the pressure or the velocity for the next iteration. Now that turned out to be very achievable inside really simplistic grids and in controlled environments, and much more difficult in the context of cars and the complexity we have to deal with. So we have, to some extent, changed direction of that, and we're working more on accelerating the flow solution via things like trained neural networks that look at how the flow should change based on its past history, but also things like initializing smartly. So in the context of a huge DOE, we're running thousands of cases. We might choose as initial condition the case that's most similar to the one that we're starting to simulate. In addition to that, I mentioned we also have coupled solvers that also fit into the project context. They're not neural networks or AI, but they still give you enormous benefits in terms of performance. So then there is an additional component which is worked on by Idiada from Spain. This is about supplementing the turbulence model. So we have two different main forms of turbulence modeling, or I mean, there's many others, but the ones that we're concerned with here is RANS or DES-LES. The one is a scale resolving. DES-LES is a scale resolving method, which is generally considered much more accurate. And RANS is not a heuristic, it's a physics-based modeling approach, but it has some approximations that mean it's less accurate in many conditions. So the idea simply here is, let's look at the results we get from the RANS modeling, let's look at the time average results we get from the DES modeling, and let's find a way to get that neural network to increase the accuracy of the RANS model so that it approaches that of the DES. i.e. we're trying to correct the error in the RANS to make it better. And at the same time, we hope that we'll get performance similar to RANS, because RANS models can run about 10 times faster than DES models. So we want to have the DES runtimes with the RANS runtimes with DES fidelity, which should allow us to do very high accuracy modeling in a fraction of the time, and allow us to generate more training data of higher quality for the neural networks. The other component then is the universal parameterization. So it turns out that there's a very useful neural network architecture that allows you to try and match your input to, or your output to your input, while constricting the data stream to a very narrow band in the middle. So if you imagine I've got something like a funnel it's big at the one end, and then go into a second funnel that expands. So you stuff in a geometry at the one end, then it goes through this very small channel at the middle, it comes out the other end. And what you want to do is to get the output of this compression, decompression cycle to look the same. And the characteristics then is that at this contracted point in the middle of the funnel, there's very few data streams. There's very few streams or very few channels with high complex or very few high complexity channels, and these act as parameters. So if you're familiar with CAD, where you have parameters that can change the radius or the height, you can extract these kind of parameters, though they don't appear at all similar, but they have a similar effect from this thing called an neural network called an autoencoder. And so doing this in the context of automotive is a big part of upscale, a big part of our work as well on the project, where we're hoping that we can extract a baseline parameterization for a large range of different vehicles by using the autoencoder, and then we can use it both to generate a vast array of test cases, or a bigger array of test cases than just the input, but we can also use it to classify new cases that the designer might come up with within the context of the neural network curve fit to the velocity data. So it plays a central role in our whole process and workflow for real-time aerodynamics. The other component there, I mentioned the battery a few times. So we're not directly involved here. This is Vrije University of Brussels, and it's essentially a reduced order model for predicting battery cooling needs and heat up through a drive cycle. So I won't go into too much detail here, but it's something that they're experts on, and they've provided us with a module to allow us to say yes or no to a particular cooling flow for the vehicle and battery pack size. Okay, so finally we get on to some progress. This is probably why most of you guys are here, to see what we've actually been able to achieve. So the project is about a year on now. We've had a few starts and stops, but I think we've made fairly good progress. The results I'm showing you now are from, I think, from October last year, so it's not quite up to date. Where things have moved along, I'll mention that. So fundamentally, those advanced methods for accelerating the solvers and you're doing the universal automatic parameterization, they're still very much under development. So what we're working with now is conventional methods where we're generating data through a simple workflow, and our geometries are generated through a conventional CAD package using baseline parameterizations. So we're using both PyTorch and Keras TensorFlow. We haven't quite decided on which architecture to use yet because they have different benefits and different advantages. I think we're leaning more towards PyTorch at the moment. And the training system is a basic unit architecture that we've tweaked slightly for our application. So the plan is here to develop these methods, these UNets, the workflows, and also the outputs and the different metrics that we use to test accuracy through successively more complicated test cases. Obviously, you want to try and get your methods robust and reliable before you go to the most complex cases. So what we've found is that a lot of these methods use a lot of memory. I think memory is the main issue here. On the GPUs, the memory is restricted and how much you can access on a single GPU, and the multi-GPU context does not work quite as well as we would have liked it. So there's some limits that we need to explore in this context. And of course, we also look at actually GPU versus CPU performance. We find that GPU is much better. So the succession of cases really go from 2D to 3D. We started with a simple wing, which we've pretty much left behind now. And then the next one is what we call the 2D driver. If you're into automotive or you're involved in the automotive sector, then you recognize this vehicle. It's kind of standard test case that people set up at the Technical University of Munich. And it's used for validating many automotive flows. So we have a 2D version of that. We have an automatic method for meshing and solving that and getting the data into the training system. And then we've taken that through the whole process. Then in order to get it to 3D, we're starting with something very simple just to test the systems, a rectangular box with some moving vertices. And then finally, we'll be looking into the 3D driver itself, the whole vehicle. This is the preliminary stage. Eventually, of course, we wanted to apply it to a real vehicle development process, but that's some years down the line yet. So this is the 2D driver and its parameterization. There are 17 parameters on this vehicle. Some of them are binary, which cause some problems down the line, but most of them are analog parameters. And we've generated several thousand different vehicle shapes using this parameterization. I think specifically this is done by CRF at FCA in Turin. And yeah, so we'll run those and then do the training based on that. You can see the different parameters, the height, the length, the front grille shutter open, close, the height as well, ride height and angles and so on. There's a lot of different parameters. So these are the base training set. I think these have been enhanced since then, but I think we now use 20% test samples, but the original set was 1,000 geometries. Some of them turned out not to be valid. Some will be used for training, and then we have about 20% for testing. The meshes are typically about 150K. That's just the box domain. I'm showing a small zoomed in image over here in the middle of the slide. And then we run steady state rounds, K omega turbulence with a fixed velocity. So it's a very simple workflow that generates the data. Once we have the flow, we make a regular grid sample of it. So you've got a 128 by 128 or 256 by 256 regular grid that's scaled to fit around the vehicle. And then we extract the velocity, the pressure, and various other components from the solution with that and pass it on into the training system. I mentioned previously we're using a standard UNet. So this is the UNet for a 128 by 128 sample size. So if you see at the top left, you have the mask input. This is a binary field. Black means fluid, white means solid. And we stretch the 128 by 128 grid so it fits to the rectangle. It doesn't have to be isotropic. And then you sample at each of these locations, whether it's inside or outside the geometry, and also whether what the velocities are and so on. And then you go through this contraction process. It's typical of these type of unit architectures where the number of input channels are decreased and the amount of, or it's not the channels, the resolution is decreased and the number of channels increases as it gets to the lower end, and then it's decompressed again to try and fit to the sampled velocity. So my input is the geometry, let's say, in the form of a binary mask, and my output is the velocity and pressure fields, and I can compute the error in my output versus the experimental, the CFD data that I've sampled to see how well or poorly my neural network is performing. There's various steps here. I'm not going to go through all the details, convolutions, resizings, and similar aspects. This is, you can read all about this stuff in this paper in the link here. If you go on the webinar afterwards, you should be able to access it. This describes in more detail this particular method. Now, of course, we've made some tweaks and we continue to enhance it, but fundamentally, this is a publicly available neural network that you can get off the shelf. Okay, so just a few examples of what this thing produces. This is one random case, basically test case 106. So there's, I think in this case there's 150 or so 120 test cases. This number 106. At the top here we have the sample of the velocity. So we've taken this sample mask of 128 by 128, stretched it over the car and into the wake, and then extracted the data. So that's why it's slightly blurred. Is because the sampling is not as fine as a typical CFD mesh would be for a case like this. But you can see in the middle image is the CNN prediction, the neural network prediction. And I was quite surprised in how good it came out, to be honest. I did not expect these neural networks at the beginning to actually be able to predict with such a high fidelity this kind of flows. Now, okay, this is a quite limited variation of cases, so all the flows have some similarity. But if you look at the statistics, which I'll show in a second, the overall accuracy is quite good. Recently, we've also done off-design studies where we've created shapes and vehicles that were not enclosed, let's say, by the original DOE, and the results are still good. So it does seem that these neural networks encode some of the physics and can predict, not just the curve fit, basically, they can predict out of parameter solutions as well. The errors here are normalized by the free stream. So you can see in some areas they are quite large. What we found is, especially here in the underhood, is that because we have a binary parameter, i.e. the open closing of the grille shutters, that was not resolved by the geometry mask, and so we got quite a lot of errors due to that. When we switch to two separate samples where we have just open grille shutter cases and just closed grille shutter cases and no other binary functions in the model, we get even better correlations. There's also, you can see near the surface, some issues, and we have some means that we plan to work on that, but it's quite promising. This is the same results, but for pressure in this case. Now, we found that pressure prediction is not as good as velocity. We're not entirely sure why, but we have some theories, but I won't go into too much detail. But you can see that broadly speaking, the CFD, or more than broadly, in a lot of detail, the CFD results and the neural network predicted results are very, very similar. There's some differences. I think if you look at the circulation, there might be some changes, and you can see some changes here in the underbody flows, but by and large, unless you look very closely, these are, I would say, indistinguishable, but they're very, very similar. And then similarly, if you look at the errors here, they're relatively small compared to the overall total pressure in the system. So this is a few statistics about the training as a whole. As I said, this is in October last year. Since then, we've done many, many thousands more trainings with many, many thousands more variations. But basically, at this point in time, we're accumulating statistics based on the magnitude of the error over the field, normalized by the local value of the predicted quantity. We have things called epochs and sample sizes, and for different variations of that. You get different performances and different accuracies, but all of them seem to converge more or less to the same level. So you have your loss function here. I don't have it on the slide, but functionally it's the difference between, let's say, the velocity, pressure vector, and the for the AI and for the CFD samples, and that's normalized by the value in the CFD. So it's a fairly standard error metric, and you can see how the error of the model that we're training decreases with the number of epochs. Each epoch has got 56 samples, and these groupings really are there to fit inside the GPU memory and allow us to train a reasonable amount of stuff at a time. For bigger cases in 3D, for example, we have to have fewer samples per epoch simply because our GPU memory can't fit anymore, and we find that multi-GPU performance isn't quite as good as we'd hoped. So overall accuracy for a case, one case compared to the mean accuracy for velocity is around 97.5% for this test case, so that's already quite good. For pressure, it wasn't that great, but then we have to remember for pressure, our normalization is much wider, so we've got a huge variation in pressures between different regions. There's some concerns about pressure in the vicinity of the boundary, etc. I should mention that since the publication of this document, we've done additional work on the system. We've improved the optimizers, we've added more diverse cases, and we've managed to reduce these error numbers to much smaller numbers. So now, right now, our velocity accuracy is only around 0.5%, 0.5%, and pressure accuracy pressure error, sorry, is down to about 3%. So we've made substantial strides since this was published. We hope to further increase the accuracy, but okay, there's a limit to what you can expect based on how much data you have and how much effort you want to put into training the model, of course. So that's where we are now. The next steps is to go to 3D. We're just finalizing right now the 2D system and doing some reporting for the project officer. The next step is to go to 3D, which will start off with a simple box. I think we'll add a few more points to make it look a bit like the Tesla Cybertruck or something, just a little bit more interesting. A box is very boring, but something like this, for example. This will highlight some issues we've been having, particularly with something like anti-aliasing, where straight lines appear to be very jagged due to the way we sample. And so we'll try and work on those issues in the context of this case. We've done some preliminary work on the cuboid. The results are broadly similar to what we achieved with the 2D vehicle. There are some higher errors. Obviously, we're not able to train fully this case on the GPU because, well, the GPU ran out of memory. So we have a lot more work to do there, either to reduce the number of channels or to somehow consolidate the memory. The alternative is to run the training process on a cluster or some kind of HPC resource. It takes a lot longer, but okay, it's not debilitatingly so. But in any case, the results, as I said, are promising. There, as you can see on these smooth surfaces, we end up with a little bit more jitter, a bit more noise. If you look at the leading edge of the cuboid, you can see this unevenness, and we think this is due to anti-aliasing issues. This is similar to what you see in computer graphics, and so we have some ideas to deal with that in future. But okay, this is very preliminary. I just wanted to show that we're making progress in the context of 3D. Errors are reasonable. They're of course we want to reduce them, but they're not out of range. And it's the same order as we had in the 2D case. It just doesn't look as smooth at this point. I think mainly because we have many fewer sample sets in the result here. Okay, and then once that's finalized, we will go to the full 3D vehicle, and we will try and parameterize that and start training on that, which should lead us to have eventually the process and methodology to create a AI model for a full 3D vehicle. So that's the end goal, obviously, and then also to build the infrastructure to give the live feedback inside a tool like Rhino or Alias to the designer to be able to make the judgment calls regarding the performance of the shape they're doing. Right. So that's brings me to close to the end of the presentation. A few more comments. Just in general, you can see the results. Well, from my perspective, the results are very promising. We're very excited about this. Recent results have shown much better accuracy, and we have a few interesting ideas to try. So we're quite confident that within a limited range of parameters, within a limited range or variations from a baseline vehicle, we can get flow feature accuracies to within the high 90 percentile points. I haven't showed you anything regarding the actual drag prediction here, but that has similar characteristics. So we can predict drag and lift on a vehicle to 97, 98%. So getting close to that 2% uncertainty that we normally aim for with a high resolution calculation. So at this point of time, we think it's very likely that this process will work, that we'll be able to provide this kind of functionality to an OEM end user that will be able to then accelerate the vehicle design process. Of course, we need more experience. There's some issues that we still have to resolve. I think mostly we're concerned about hardware limitations at the moment. So we know we can run on CPUs, we can train on CPUs, but then the training will increase by cost will increase by an order of magnitude. So you go from a day to 10 days or more, and that's an issue. Of course, we also have to try and get high fidelity data for the 3D models, which is more challenging because running an LES or a DES calculation on a full vehicle can take several days. These small 2D cases take a few minutes to run, and that of course will increase. We have means to do that, but they're still being developed, and we are not confident yet what the outcomes will be. Then the process is still under development, of course. We're looking into the pressure issues, why that was poorly predicted. Currently, it's predicting better, but it's still not as good as the velocity. So we just like to understand what is going on there. And also we have issues with surface representation. So you can understand that if I'm sampling a CFD solution with a set of discrete points, a regular array of discrete points, sometimes a very small motion in the surface could mean that a point is inside or outside the solid part of the model. And that kind of hysteresis, that kind of aliasing effect is problematic, and we need to do something to make that more of a continuous function, because the neural networks do not deal well with discontinuities, as I mentioned at the beginning. So beyond that, streamline, integrate, we're pretty close to deploying the baseline systems now, and we'll see how things progress from there. Then is in a more philosophical sense, where it's all going. The promise is obviously huge. We've seen other people implement very interesting things in the context of artificial neural networks. The predictive power is unquestioned. If you have the data, it can predict similar occurrences. It requires much less domain knowledge than physics-based modeling, which is both a blessing and a curse, I think. So these neural networks can predict the stuff, but it doesn't always provide you with an explanation. We understand that if it can predict out of design or outside of its training environment, then it must encode some of the physics. It must contain some knowledge, and that's really where the challenge will lie, I think, in future, is how to get the knowledge out of these neural networks, how to understand what's going on rather than just blindly predict what is going to happen. Because I think that in order to make the big leaps, the big discoveries, we need to understand. And there's some interesting work being done in this direction. Something called explainable artificial intelligence looks very promising, but I think that's really where we need to do a lot of work, a lot of thinking, is how do we leverage what the AI is learning to make us more experienced and us more knowledgeable about the subject as well. So that concludes my presentation today. Thank you very much. If there's any questions.
All right, thanks a lot, Eugene. We have a few questions. I'll start out with, what's your strategy for generating training data in a 3D Aero-Thermal case?
Well, of course, as I mentioned, the costs go up substantially when you go from 2D to 3D, and it depends also on the fidelity you want to achieve, and how accurate do you want this to be with regards to your wind tunnel, and how much are you prepared to pay. But the strategy is essentially to accelerate the process of generating data via both machine learning. So we want to use RANS models, which are fast to do the 3D modeling, but those RONS models, if they need to be accurate, they need to be augmented with AI that's been trained on DES or LES high fidelity data. So that's an ongoing process within the project. And if we combine these various components that we're working on, I think we can achieve both a wide range of solutions, so a wide range of data, but also do so in a short amount of time.
Gotcha. Another question. Let's see. So at maybe a more basic level, this questioner was interested in using AI to data mine the thousands of CFD runs that they generate during a typical vehicle program. Is this something that you could comment on? So data mining on existing runs.
Yeah, I mean, of course, that's essentially what we're doing. We're just doing it artificially here because we're trying to build the system and prove the concept. But that would be a perfect utilization for this, to try and, let's say, encode that data into a model so that you have easier access to it and you can use it in a much more value-add context. So you could conceptually go, and every case that you run, you don't have to necessarily store it entirely, but you could go and sample that case at a specific level, store that knowledge or that data, sorry, and then go and train an AI based on it. That would then allow you in a future vehicle program or at a later stage of the same vehicle program to go and probe small variations potentially or small changes relative to the baseline. And the more you feed this model, the more data you give it, you could potentially have a wider range of applicability as well. So there's not quite sure where the limits lie, but certainly I think in the context of mining all data, yeah, if you've got it in sufficient resolution, I think that's a very valid use of the technology.
Okay. Another one is, how will this be productionized? What are the challenges going from 2D to 3D in terms of the network?
That's what we're trying to answer right now. I think that the network we don't expect will change that much. We've already built the 3D network. There's certain challenges relating to surface fidelity. So as I mentioned a few times, the idea of using anti-aliasing. But productionizing really for us means building a front end, a plugin for Alias or Rhino, really, and that plugin or interface will then contain the AI model. And we would like the designer to stay inside their design environment and see numbers changing, if not in total real time, close to real time. So you should be able to make a few changes. Either it updates itself automatically, or you press a button and then a few seconds or minutes later it tells you, okay, this is good or bad. That's the vision of this particular project. So that requires quite a few things from our end still. So we're quite some ways off, let's say, deploying this into a design studio. But I think even before, let's say, a flashy implementation like that, so where we have it fully integrated into the design tool, we could have something where the designer could export the surface and run a script or run some experimental, something a bit more prototypey to start getting some results. So whether that will be acceptable or not, I don't know. I haven't interacted with that part of the vehicle development process that much, but we certainly have various points at which we could start to bring it into the process, and it really depends on what people are comfortable with using.
Okay, excellent. So another question we have, so are you going to be limited to RANs, or do you have plans for DES training data? You already touched on this, but maybe it's good to answer this one again.
I mean, we would like to be able to use DES training data, but it would require some form of acceleration. I think that we're looking at something approaching 1,000 cases that you need to do, and this is not different wind directions. It needs to be 1,000 geometry variations around a theme, and they need to be representative of what you anticipate will be changed by the designer. It doesn't have to be exact. It doesn't seem, our experience so far indicates that as long as you're training in the general region, then it'll figure out what to do, but you need a lot of cases basically. And so if you think that if I'm running, I don't know, 150 million cell DES or 200 million cell DES calculation on 1,000 cores, that'll take, I don't know, maybe 30 hours or so with our technology. that might be prohibitive if you're let's say you have 24 hours per case, you want 1,000. It's 1,000. 1,000 times 1,000 cores times a days, or so, but it's a million days worth of, right? No, it's a million CPU days. So that could be quite expensive, but maybe that's warranted. I don't know. I mean, it really depends on how much computational investment you can make upfront in the vehicle design process. What we would like to do, one of our ideas, and one of the I think that's quite novel about what we're trying to do, is to try and cut that DES cost substantially. So we want to keep the accuracy of DES, but we want to run a little bit faster. So we are very time step limited at the moment in terms of how we run DES, simply because if we run at larger time steps, the numerical diffusion starts making things inaccurate. So we would like to try and use the AI to correct that error and allow us to run at larger time step, let's say 10 times larger time step, and then correct some of the error in the modeling that comes from the diffusion. So we're quite hopeful that that approach will allow us to cut that cost by an order of magnitude, and that will make it very realistic for us to run DES for these training sets.
Excellent. Now the question is, what was the grid resolution in the 3D cases? So I don't know if this is related to the CFD or if this is related to the mapping.
Well, I can for both. For the 3D case, we hit on our available GPUs, we hit limits with 128 cubed. So there's some severe sampling size restrictions for GPU usage. So now there are bigger GPUs coming along, and we did not use the GPU with the biggest memory availability on the market currently. So I think we could quite easily fit the 128 into a top of the range Tesla card. Ideally, we would like to use 256. That gives us a resolution of some features that are important to the aerodynamics, specifically grill shutters and underhood flows. We're not sure whether that'll be feasible. In terms of the CFD, the case I showed was just was a relatively coarse. The box was relatively coarse, so that does not really representative of the kind of cars that we would run. For RONS or DES, we basically make the same meshes these days. So that's 100 million, 150 million typically for a small sedan. It could be bigger for an SUV. So yeah, I hope that answers the question.
All right, excellent. And then you mentioned this a little bit earlier, wind direction, but can these developments for automotive be applied to other industrial applications outside of automotive?
Oh yeah, definitely. I mean, we had a user group meeting last year here in London, and one of our customers, Foster & Partners, they presented an application of this technology to wind engineering. Again, this is a field where accuracy is not paramount, but they need speed to be able to predict pedestrian comfort. So they had this whole system whereby they train the neural network on flow around cubes and boxes and similar shapes reminiscent of buildings, and they use the neural network to predict flows around much more complex combinations of these shapes. And they were even able to use it for inverse design, where they asked the AI or the neural network how to change the building design in order to get particular flow patterns. So yeah, there's definitely applications outside of automotive. I think anywhere where you have a lot of design loops, where you have optimization, anywhere where there's experience and knowledge embedded into systems, this thing can be very valuable.
All right, excellent. I think that's it with the questions. If you have any questions after this webinar, feel free to reply to the meeting invite and I will take care of it. I'll reply, or we'll have Eugene or another engineer here at ENGYS reply. Again, Eugene, thanks a lot for presenting today, and thank you everyone for attending.
My pleasure. Thank you, Dan.
Thanks a lot. Yep.